we aspire to do is try to help people be on the cutting edge and help those users that maybe don't want to develop the cutting edge also be on the cutting edge or as close as possible. So I wanted to start off first with, with who does the work. I haven't done any coding for more than a decade, and Georg and John, Jacob, Lawrence, and Mitchell are really the core ScanImage team. As far as I can tell, Georg and John can do pretty much anything in engineering, whether it's mechanical, software, or electrical. Jacob is also a really talented engineer. He does a lot of our support stuff, but he also develops a lot. Lawrence is from University of Maryland, really hardcore software engineer, and Mitchell helps out on the support side. And so those are really the people that make ScanImage happen on a day-to-day basis. And I do want to include these other people though, because Scientifica, Thor Labs, et cetera, do a lot of testing on their systems for us. And we've already talked about Bruno and Dale with INSS and COSIS, and they give us a lot of suggestions, tell us where we're messing up, and we appreciate any of that kind of feedback that we get from people in the field, so including users. So please do give us feedback; it's really important. And I wanted to highlight there's a new microscope company out there, Prospective, that might be interesting. They're trying to go on the clinical side, and they've got a laser integrated into the scan head. So it may not be good for the cutting edge, but it might be interesting on the clinical side. So what is ScanImage? Well, it's a laser scanning microscope software per se. A lot of people use it for 2-photon, but there are a few people that do confocal or other types of laser scanning applications. It's based in MATLAB. The MATLAB part is open source and user customizable with a fully scriptable user interface. And it's compatible with, any of those sort of home built types of systems you might do. And I think I can say that we've probably run ScanImage on almost all commercial scopes as well at this point. One person or another is asked to have it, have their scope run ScanImage. And one of our favorite things to say is don't let the microscope control you. And so we try to give you the flexibility to do what you want to do with your microscope. A lot of people, are trying to do those novel things like imaging the spinal cord, and there's probably special things you had to do, to really get that to work, right? So that's our funny little saying, but we hope we can really live by that. So a little bit of history lesson. ScanImage been in development now for about 18 years. It originated in Carl Swoboda's lab at Cold Spring Harbor. Thomas Polagruto and Bernardo Sabatini were key developers, as well as Carl himself. There was a paper published in 2003 describing this software, and it was really focused only on what people term linear scanning, which is 2 galvos driving, the raster scanning approach in an XY fashion. And there were a couple of iterations of that. In 2011, the first Resonant scanning application was developed. This was done a lot by Vijay Iyer, who actually is one of the founders of Vidrio back in 2013. And SI4, that was called SI4. So linear scanning and resonant scanning were in separate applications up until that point. And Carl and Vijay, I think, would say that they made a mistake because SI4 was only compatible with this Thor Labs system, and it lost some of its flexibility as a result of that. So in December of 2014, the first application of ScanImage variety was released that could do both linear and resonant scanning. It was called SI5, and that morphed into a full-featured version where we've had about 2 releases a year since 2015. So what does this kind of software have to do? Well, it has to control all these different types of devices, right? It's got to be able to control the galvos and shutters and Pockle cells to control beam power, maybe a half-wave half-wave plates, or it's got to acquire the signal and condition it. Maybe it has to do camera acquisition, control SLMs. I mean, there's a lot of complex things that the software has to do. And furthermore, we've tried to make it as flexible as possible, right? So you can start with OEM parts, you can start with scanners and stages and your own piezos, et cetera. You can go from kits, you know, there's several companies that offer kits. You can work with INSS and COSYS to build a custom microscope or do it yourself. But there's also these finished scopes that, you know, that Scientifica and others, you know, offer. One of the things I would point out, I mean, there was some discussion over the last couple of days about, you know, well, how do we get some of these techniques into the average user's hands? And Thor Labs and Scientific have tried to put SLMs into their microscope. So there's some, you know, efforts going on there. Both of them have metal arc SLM capability. The Scientifica one just got released this year. So if you want a more finished kind of approach on an SLM, that might be a path for you, worth looking into. So what kind of scanner combinations can ScanImage support? Well, there's the typical galvo-galvo type of operation. That can be used for imaging or photostimulation. You know, back in the early days, you know, just driving like circular spiral patterns over cells, as Darcy was describing yesterday, with more sophisticated version with an SLM, was done in series. You can image about 2 to 3 hertz with you know, with a galvo approach. The resonant scanning approach combines a resonant mirror with a galvo, and you can get into video rates that way. Obviously, with the more fancy types of things that people have been describing, you can go faster with dividing up the you know, multiple imaging planes and that type of thing. There's another approach where you can go faster with, you know, combining a resonant and 2 galvos together, an RGG type of approach. You know, people have demonstrated you can go over 100 hertz frame rates with this by looking at little postage stamp areas rather than the whole field of view. And then, you know, the most complicated types of systems, you can have dual scan paths or more than dual scan paths, have photostim on one, imaging on another, add SLMs and that kind of thing. So ScanImage is very flexible, support all of these types of things. So just to give you kind of a feeling of what that means on the software level, you know, a typical analog signal profile for a resonant scanning volume image might look something like this, where you've got, you know, in the blue line, a fast Z piezo, where you've got a trigger that triggers off a voltage, a linear voltage increase that sends the piezo in a Z direction. And then you've got a Y galvo, where it's scanning in the Y direction and then flying back with, you know, triggers to start each of those scanning motions. And then a Pockle cell that's turning the, you know, the laser beam power on and off at the edges of a linear scan. And then of course you got to keep that in sync with the resonant scanner, which maybe doesn't always show up right at the same time every time. It's not as deterministic. So this gives you an example of the kinds of timings that you have to be aware of and the types of analog signals that you're going to have to send out to control devices. This is a relatively simple one, but it's kind of a standard approach. So here's a history of the hardware that's been used with ScanImage. It started off with in SI3 with this NI6110. It's a PCI form factor. It was only made for galvos. You might notice that there's this connector back here for a RITSI cable. If you put in another card because you needed additional analog outputs, for example, you'd have to communicate over the RITSI interface for the timing events and things like that. The SI4 was based on this Alizar card, which is also a PCI form factor. And then to really make it more flexible, as we launched the initial ScanImage at Vidrio, we decided to go with this NI PXIe chassis, and has a lot of positive things. It was a PCIe form factor, had a lot of configurable cards you can slide into the slots of the chassis, and it was a good replacement initially for the Alizar cards for resonant scanning. You could get a nice FPGA for resonant scanning, for example, on one of the cards. We did run into limitations over time, and we tried to work with NI to develop cards that got rid of those limitations, and ultimately we wound up developing our own card, which is called the vDAQ, and so I'll tell you a little bit more about that. So we still support the NI chassis and the NI hardware, but we think the vDAQ is superior, and there'll be features that get developed for the vDAQ moving forward that probably won't be capable to be implemented on the NI hardware. Just to go into a little bit more detail here, there's two boards here on the vDAQ. Actually, there's a main board and a daughter board. The main board contains, sort of the common workings. It's got 12 analog inputs, each that are 16-bit per channel and 1 megahertz, and 12 analog outputs that are 16-bit and 2 megahertz sampling. So all of these are independently timed, and this was one of the limitations with the NI hardware, is that when you get a 6341 card, for example, the analog outputs do not have independent timing. So you always had to kind of overbuy analog outputs and NI hardware, for example. Another key thing is that this has the newest ultra-scale FPGA on it. It's got 4 gigs of RAM, and it's also got the ability to synchronize with external laser clocks from 1 to 425 megahertz. This is coupled with onboard clock synthesis, which can multiply and phase delay input clocks in a really elegant way. So the other thing is the daughter board you can get in 2 varieties, one that has 4 analog inputs at 125 megahertz, and then another one that's just been released in the last couple of months that has 2 analog inputs at 2.6 gigahertz. And there's some specialized, high-speed applications that I'll talk a little bit more about that you can do with this high-speed ADC. And I think one of the things that's really cool is this high-speed data transfer rate. So just to talk about that a little bit more in the next couple of slides, the ScanImage architecture is laid out like this. There's an acquisition engine on the FPGA. There's 2 threads running in C++, one that writes the data out and one that's a data transfer thread. And then the data gets transferred into a MATLAB thread. So there's really only 3 threads running, in the software as a whole. And when you look at the hardware level, this is what it looks like. So you've got the C++ and MATLAB code running up here in the CPU. There's a kernel driver, mode driver here that communicates with the FPGA. But one of the really exciting things is that you have this lossless 4 gigabyte per second data transfer rate that goes directly from the board to the computer memory without going through the CPU. And one of the things that I was highlighting the other day, is that we envision that this would also be easy to implement for directly into the GPU memory as well. We just haven't found an application to do that where the speed of that is really required yet. So, but that is something that should be relatively straightforward to do if anybody really thinks that they need that kind of speed. So just kind of summarizing. Oh, go ahead. Somebody have a question?
So with this type of paradigm, would you have access to the frame just when the capture is over? So basically where all the frame was captured, or do you also have access to, let's say, half of the frame as it is captured by the data acquisition board?
This is Jonathan King. I'm going to jump in here. You would absolutely have access to the frame partially as it's being acquired, and depending on whether you implemented some algorithm on the FPGA or in the C++ backend of the ScanImage code, you could have, obviously different levels of latency from when the analog signal of the pixel is actually acquired to when you perform some operation on it. But the bottom line is, yes, you can do operations on partial frames.
That's nice.
Does that answer the question?
Yeah, absolutely. Thanks. But this would be available through the MATLAB interface or through what exactly?
It wouldn't be available through the MATLAB interface since the C++ backend of ScanImage intercepts the data first, just to make sure that the performance is adequate to make sure all the data gets logged to disk. And the ScanImage architecture, not all the frames get processed through MATLAB. So if something needs to operate down to the level of partial frames, it would have to be in C++ or in FPGA.
But right now, it's not, we don't have access to the C++ portion of the code, right? So if we need to implement something.
That's correct.
Yeah, I think, Andrea,
that's correct. The C++ is not open source.
No, not for the open source. That's fine. Just to have access to it in some way. It doesn't need to be open source, but maybe have a port or something that we can access to then collect this data. That would be very useful.
So I think, Andrea, that you may have talked to Georg about this in the past, and I think it's a really good idea to try to put in a TCP connection into the C++ layer. I think that would give you what you want. I mean, we were worried before, I think, when we talked that, you can access the data from the MATLAB layer, but as John mentioned, it's not lossless, right? Because sometimes MATLAB falls behind, and to make sure that you get lossless data, you've got to get to the C++ layer.
Cool. And in terms the other questions that you said, I don't see a scenario where it would be necessary to pass things directly to the GPU. Am I correct in the? I seem to remember last time that we chatted, not with you, maybe with somebody else, that you were also looking into voltage imaging, right? To add acquisition. I don't know if it's gonna go through the same type of acquisition board or some other acquisition type of acquisition. That's definitely a use case that you might want to transfer to the GPU.
Okay, that's great feedback. Thank you.
No problem. Thanks.
So just to kind of summarize that hardware part up, you've got, the C++ code, the MATLAB code up here in the CPU, running with, an interface. For the NI hardware, you've got these two drivers, the NI Rio driver interfacing with the FPGA boards, and then the DAQ-MX driver interacting with the DAQ boards. And this is one of the other limitations of the NI hardware, is that the communication between the FPGA and these the DAQ boards has to go through a backplane, and there's limited number of channels, and there's limitations on the speed and a variety of other issues. And with the vDAQ, we got rid of all of that. It's all on the same board, and you've got immediate interaction between the FPGA and the analog outputs and analog inputs, et cetera. So we felt this was, really necessary to get to these types of closed loop things that people were going towards in the future. One of the things we've worked on hard over the last year is to try to make it easier to add devices into your system. And that's always been feedback from people that, oh gosh, it's really hard to configure ScanImage. And so there's been a lot of work on that. There's now this resource configuration interface where ScanImage, you have a ScanImage tab and a device tab. Here you can add devices. There's a whole list of compatible devices when you hit the plus button here, and then you can configure them individually. You can know whether they're working or not, and you can see here this one's highlighted red. That means my PMT is something's not configured correctly about it, and I need to fix that. And so this really avoids like the past, the really healthy criticism in the past as well. I configure it, and then I get these errors thrown in ScanImage. Well, this really helps you figure out if your configurations are correct ahead of time. And then you can build, these different imaging systems. it might be better to call this scanning systems here, because it could be a, you know, a photostim scanning system, for example, but you can configure a variety of these, multiple ones, switch between them in the interface, for example, as well. So this is basically building on the components that you have as devices. So one last thing about this new resource configuration is two things. One, you have these widgets now on the side, and you can literally move these little you know, tools around and test whether the galvos are working. You can see the resonant scanner is working. You can open and close the shutter by clicking here. You can turn the PMT on and off, and oh, look, this PMT isn't configured correctly. It's highlighted red, so I can double click on this and pop up the PMT configuration and try to figure out what's going wrong with it. In addition, you've got this whole vDAQ panel here if you're using a vDAQ, and you can pop up a test panel and run all kinds of tests. Here's a picture of the breakout board. You can click on this breakout, and it shows you exactly how you've configured everything, right? So I expect my RMR, you know, or my galvo control to be here, and my X galvo feedback to be here. And so it makes it a whole lot easier to you know, set the microscope up, hopefully. These are things that we've been working on to try to improve, you know, the usability. This is a huge list of features that comes from our website on, you know, from ScanImage. And, you know, I'm not going to have time to go through all these, but I did want to highlight a couple of things. There's 3P support. There's been a lot of discussion about SLM and 3D shot. We worked with Nico and the Desnik lab to put that into ScanImage. There's a lot of people talking about big files. Well, we support big TIFF, so you can make big files. Not everyone wants to do that, of course. You know, so there's a lot of different features in ScanImage that you can take a look at, and we just reworked our documentation, and you can find that at docs.scanimage.org. And if you want to take a deep dive into what those features are, you can do that in the doc. So please look at that, give us feedback if you see that we've missed stuff in the new docs. So now I want to shift into some features, and John, I forgot to mention John's on. Sorry about that, John. He's going to actually run some live demos to show some of these features. The first one we'll spend a little bit of time talking about is this multi-region of imaging approach, and it really allows you to do flexible stack and volume acquisition. This is a video from Aaron Curlin where he wanted to follow you know, a dendritic tree structure, and you can see he drew little postage stamps and followed that and tried to follow the activity you know, of this particular neuron he was interested in. There's also the ability to do laser scanning photostimulation. There's all kinds of patterns you can apply here. You can put in your own patterns if you want. You can do these spirals. You can even do Mickey Mouse if you wanted, as a fun thing that we always put in there. You can do real-time image analysis and motion correction with the stages. You know, it's hard to do fast motion correction, as you guys know, depending on what your imaging rate is. So, you know, there are limitations for those reasons. There's also 3D motion correction, which is mostly, you know, slow motion like drift can be corrected for. And then there's also support for closed loop experiments, and we'll talk more about that. And we can show you a little bit about how, you know, you would configure ScanImage to fire a trigger to do this type of closed loop experimentation. So I did want to highlight two things that have been, you know, projects, the customizations that happened with a couple of labs. So one is this timestamp behavior. So when you're doing behavior experiments, you need to have tight synchronization between your imaging and your behavior device, whatever it is. And the Tank Lab came to us and said, hey, we want to be able to use I2C packets to record events from our behavior apparatus. And so we did this project with them. The behavior device generates these packets, the I2C packets. The FPGA ScanImage part can evaluate and timestamp them, and the accuracy is better than 100 nanoseconds in terms of synchronization with this. So you get into that sub-microsecond scale with this kind of system. This is the way the Tank Lab does it. Other people have done it differently, but this is a really cool I2C approach that we thought was clever that they came up with. Another thing that Darcy talked a little bit about yesterday was temporal demultiplexing. The new high-speed vDAQ with the 2.7 gigahertz ADC has this kind of capability, obviously, and here's a simple approach of that, where you would split the laser pulse into two and delay one by 6.25 nanoseconds. Of course, with an 80 megahertz laser, you've got 12.5 nanosecond window between pulses. So you'd split the beam, delay one, and then image in two places. And then the data comes in, mixed, and then you can demultiplex that, with this kind of high-speed data acquisition approach. So the new vDAQ at 2.7 gigahertz can, divide up that 12.5 nanoseconds into 64-time multiplex channels. And, this type of approach is, as Darcy talked about yesterday, is being pioneered by Ali Pasha at Rockefeller. And, so we've helped him, with some of that stuff that he just made the preprint with, and he's taken it to the, trying to take it to the next level now. So this is a really exciting approach, in our opinion. So now I'm going to dive into some detail, and John's going to do some demos. So this is just multi-region of interest. So basically, the fundamental problem is, how do I, speed up imaging is one thing that people want to do. So if you target, multiple areas, and you can do this with galvos too, by the way, but you're just not going to go as fast. So to really do this effectively, you have to have a resonant galvo-galvo configuration. So you can target an area with the X galvo and then use your resonant Y galvo scan to scan, individual areas within the field of view. So each ROI can have a different size and resolution and power characteristic and principle. You can also do 3D, different types of 3D volumes, specified. So it can be a really powerful approach from that perspective. You can change the size and position with depth, potentially even. So one of the really big applications of this was on large field of view microscope. So here I'm going to highlight Nick Safroniu's mesoscope work in Carl Svoboda's lab. And here the goal was to be able to image and stimulate activity across multiple cortical columns. And so there's a 5 millimeter field of view in this microscope with a special objective. And they wanted to have subcellular resolution with a 0.61 micron lateral point spread function. And they needed to have random access with a resonant galvo-galvo scanner kind of approach. And then ultimately they combined this with a volume imaging with remote focusing, so that they could do a 1 millimeter focus range with the remote focusing systems. So the challenges here are that, with a typical 2P microscope, you got about a 500 micron field of view. This has 10 times that, right? If you want to achieve diffraction limited resolution with the resonant scanner, you can only cover 610 microns in the lateral direction. And then you'd obviously have to scan the full Y galvo scan to cover that, the 5 millimeter field of view. But you can do that at a particular scan rate. But then an additional X Galvo will allow you to move off axis and do, another collection of data. So ultimately, that gives you this ability to make a composite of the entire field of view so that you can, view the entire 5 millimeter field of view. And if you haven't seen these videos from Nick, here's one. He's imaging 5 millimeters of a mouse brain. He imaged the whole brain with that tiling approach that I just showed. And then you can zoom in with, this very good resolution, and you can monitor the activity. This is post-analysis, post-imaging analysis of, of tens of thousands of neurons with this approach. And I got to tell you that when I've worked in a lot of fields of science, but when I saw this video from Nick, it really blew me away. And just the ability that you guys have created in the neuroscience community to do this kind of thing and correlate activity with, with behavior it's going to change everything. So I'm going to turn it over to John now so that he can do a little bit of a demo on the ROI stuff. So John, you want to take it away?
Sure. Can everybody hear me?
Yep.
All right. I'm going to go ahead and share my screen. Okay. So yeah, I just want to kind of reinforce and demonstrate some of the things that Bruce was just talking about and kind of really highlight why the multiple region of interest imaging is really effective here. So, so I'll start out just by focusing on my sample here. We have a interesting brain slice that we can image here, and I have a motorized stage that it's connected to. And you can see with a typical 512 by 512 image, my frame rate is 30 Hertz. If I combine that with a volume scan, I'll go ahead here and set up a volume scan to capture kind of the depth of the sample that I'm interested in, and set my start position, set my end position. You guys might already be familiar with this interface. So if I then divide that into 10 slices and enable my stack. So now, even though my frame rate is 30 Hertz, since I'm decimating that by how many slices I'm imaging, I'm only getting a volume rate of 2.73 Hertz, which is not great. So if I'm looking at a sample like this, and I'm only interested in very small regions that are distributed amongst the area, then it's much more effective for me to only focus my scanning on those regions, and that way increase my frame rate. So to do that, I'm going to go ahead and open up the ROI editor. And within this interface, I can grab a snapshot so I have some context of what I have within my field of view and use that context to draw my ROIs with. And in this interface, I can traverse this projection view to see what I can image throughout the depth of the sample. So let's maybe focus on a small region right here. I can add a new ROI. And say I'm interested in this little area here. So you can see in this projection view that it's showing that this ROI is kind of exists everywhere throughout the Z of the sample, but I can actually constrain that. So perhaps I'm only interested in this particular feature throughout a certain range of Z. So if I define this scan field for this ROI at 2 points, you can see now this interface is showing me that this ROI only exists between those 2 points where it's bounded. I can also, like Bruce mentioned, control the shape of this ROI through Z. So if the feature that I'm interested in kind of has some, different profile throughout Z, I can control for that so that I stay focused only on what I'm interested in throughout the depth. And so you can see that I've defined it at several places, and between where I've defined it, it's interpolated. So that's kind of the power that this interface gives you. And then of course you can define multiple ROIs. So perhaps at some other Z planes, I'm interested in, some other features over here. And as you can see, again, since it's only defined at one place, this ROI is everywhere in Z, but I can also tell it I only want it to be imaged in one Z plane by turning on this discrete plane mode. So now that ROI will only be imaged at that slice. And maybe I'll define some more ROIs here. So that's the power that this interface gives you to define your ROIs. If we now go back and image these, let's see what that looks like. So I'm going to enable multiple region of interest mode and focus. And now that you see with that simple ROI setup that I've defined, and actually I shouldn't have done a focus, I'm going to do a grab. So with that simple ROI setup that I defined, my frame rate is now 239 Hertz, and that's decimated by the volume rate. But even then, I still get decent rate. I have a 15 Hertz volume rate. Obviously, this display mode is not the most effective for imaging these ROIs, but we have a couple different ways that you can visualize the acquisition. So if I go into 3D mode instead of tiled, I can kind of see these in a 3D context for where they exist in the sample. Still, depending on what you're looking at, not the most effective. So another thing you can do is right click these and say, add to my scan field display window. And I have this window that'll show me just focus on the ROIs that I want to see. So that's just a few ways that you can utilize the multiple region of interest feature. Like Bruce mentioned, Aaron Curlin used this kind of imaging technique to image entire dendritic tree structures and getting upwards of 10, 15 Hertz volume rates, which is pretty great for doing volume imaging where normally you're limited to something much slower. So I'll go ahead and turn it back over to Bruce at this point and let you continue. And of course, if anybody has any questions, feel free to jump in right now.
All right, can everybody see my screen again?
Yes.
Hopefully. Great, thanks. So now I wanted to just highlight a little bit about activity integration and closed loop control. So this this is a movie from Genelia, and this shows the an image over here that's ongoing in real time of a live awake animal. And then this is the actual reporting interface for the region of interest activity integration monitor. And so you can see 50 different regions of interest were defined here in some way. And then this is a heat map showing where the activity is, yellow being high activity, blue being low. And then two areas, two neurons were highlighted here for whatever reason, just as an example. And I think you'll see this one fire here, and you get a nice heat map location here. So you can monitor, lots of different things. You can then also set up trigger events that would occur based on activity of your region of interest. So I think, there's a lot of discussion about trying to do closed loop stuff. And, so John's going to now demo, how you would set something like this up. And it's actually not that different. You can use that region of interest type of interface, or you can define your own mask. If you have a way of segmenting the cells, or you want to load in a mask that tells you where exactly where you want to monitor, et cetera. So John, you want to take it away again?
Sure, thank you. Okay, so again, I'm back to just regular 2D imaging, and you can definitely combine this feature with the multiple region of interest imaging technique. For now, I'm just going to do it, with a regular full frame scan. So I can open the integration controls here, and I can edit integration fields. And like Bruce mentioned, this is going to open in the same ROI editor. And just a moment, let me clear out the existing snapshots and clear out the existing group. Let's see. Okay. So now if I start my focus again, pull up my main controls, just like before with when I'm drawing my ROIs for imaging, I can grab a snapshot here so that I can draw my ROIs for integration. So if I add ROI, I can draw these regions for analysis. And actually, I can't do this while imaging, so I'm going to stop imaging. And I'll draw a few regions for analysis. And this feature will work up to hundreds of different regions. It's pretty flexible. Like Bruce mentioned, you can plug in your own algorithm or use the built-in algorithms to actually segment cells in the image so that I can automatically just detect all the cell bodies that I want to monitor activity for. Now that my regions are defined, I can turn on this integration, enable the integration display. And now when I focus, I show the integration display, it's showing me live activity traces for all the regions that I selected. And you can see in the image here, as I hover over these different areas in the heat map, it's showing me which ROI is being displayed there. I'm going to do a simple demo to show this display working. I'm going to use the power box feature to turn up power in one of these regions just to show that the display here will see that activity. So using the power box feature, I've just defined a small region here where I'm going to increase the power. So when I turn the power box on, you can see we're now showing some activity in that zone. Like Bruce mentioned, we can combine this with the closed loop capabilities, and that's what the bottom half of this interface is here. So if I go into my microscope configuration, the interface that Bruce mentioned earlier, I have the ability to create these integration outputs. And these integration outputs can use any of the outputs on the vDAQ, either an analog output or a digital output. And this interface allows me to specify what will happen on that output. You can implement a custom function that will receive all the information about the intensity in all the ROIs and will calculate what to output in the specific output that you've chosen. In this case, if we go back to the configuration, I have selected a digital output, the 3.5 on the vDAQ. And so this integration function is just going to output a signal of true or false, whether or not that digital output should be high. And in this case, I'll just select our favorite ROI. And so this simple formula says if the mean intensity for that, all the pixels in that ROI are greater than 1000, the output will be true. And to demonstrate that that's working, I'll just show this breakout interface. And this has these live indications to show you the state of all the digital channels. So we should see that light by the D3.5 turn on when we have our activity. So if we then go back to focus, and I'll use the power box feature to simulate some activity in that ROI. When I turn the power box on, you see that our trace goes high. We see that blue light by D3.5, and I'll go back off when the activity goes away. So again, this is flexible. You can implement your own function here to process and determine what to send to the output. And if it's an analog channel, you can output an intensity signal that's proportional to the intensity of the activity in that ROI, or any kind of complex formula you need to make your experiment work. And then you can take this trigger and trigger some closed loop aspect of your experiment, whether it's some kind of reward circuit or anything else. So that's just a few ways that you might utilize this interface. So I'll go ahead and turn it back over to Bruce.
I have a quick question. I don't know if it's a good moment.
Yeah, go.
So when you generate holograms, right? what type of algorithm are you using? Because, you know, in general, these algorithms are very time consuming, especially as the number of points that you want to, you know, modulate increase, as Nico showed like in the first day. So what is your approach here to generate these holograms?
Well, for the SLM feature, I think the only thing that's supported is the you know, the one that Nico showed. What's remind me of the name? It's the inferior one that's sort of the standard one. But you can
Gerber-Saxton.
Yeah, thank you. So it's that standard approach, but you can plug in your own equations as well, right? So I don't have any experience, or I don't think we have any experience in trying to compute more complex things, you know, to be able to give you any estimate of that timing and how it would function, right? But gosh, that'd be great to collaborate on if you guys want to try that, or if Nico wants to try it, right? I mean, you know, I think that it's really exciting to see, you know, these really better patterns that, you know, that deposit more power in the right places. So, you know, if we can make it work with ScanImage, that'd be great.
Yeah, that'd be very, very, very great, actually.
Yeah.
Okay, I'll get in touch with you then.
Okay. So the next thing on the list is photon counting. So one of the things that the new high-speed vDAQ allows you to do is photon counting. And so there's a signal conditioning control interface that John will show you in a minute and give you a demonstration of. But I just wanted to highlight one thing where Kyle Lillis at Harvard has been trying this out, and he's actually been trying to compute some lifetime. So he's been using time correlated single photon counting to provide lifetime estimates. And so he's got the sensor that detects chloride concentration changes in a fret configuration where the yellow YFP over CFP fluorescence is proportional to chloride concentration. But when you're imaging in hippocampus, I think there's a lot of light scattering issues that happen, and this can affect the calculation of this proportional ratio. And so he's been exploring whether he can do lifetime. And it turns out that CFP lifetime is also chloride sensitive. And so he provided these images from some preliminary work he's been doing, showing, you know, he was able to calculate CFP lifetime images, and it correlates, you know, well with this intensity ratios, at least on a first order approximation. So he estimates that lifetimes greater than 1.5 nanoseconds can be estimated with, you know, the high speed vDAQ. So I guess, you know, we're interested in feedback from the community about how useful that might be. You know, he wrote all his own software to do these lifetime estimates. But John's going to show a little demo on how to do the, you know, the photon counting now.
Yeah, before I jump into the demo, I also just want to add to that you know, Kyle has highlighted some of the advantages that the high-speed vDAQ has given him compared to something like a Becker-Hickel or a picoquant system. When doing the photon counting with the Becker-Hickel system, one of the things you have is dead time from when a photon is detected till when you can detect another photon. The high-speed vDAQ doesn't have that issue, and I'll show you, you know, demonstrate why that is. And so basically what he's finding is that he's able to collect a lot more photons over a shorter acquisition time, which means it takes less time to generate a more accurate lifetime estimate. So, you know, he's pretty excited about the capabilities that the high-speed vDAQ is giving him. And, you know, we at Vidrio are definitely interested in seeing how this tool can help improve people's research in the fluorescence lifetime area. So let me go ahead and share my screen here and show you what the photon counting feature looks like. Close up some of these windows. So like Bruce mentioned, we opened the signal conditioning controls in order to configure our photon counting. And I'll start imaging just so we can grab some interesting photons on the screen. So this allows us to, even during the acquisition view what's going on the PMTs in real time, and see if I can get a trace with a lot of photons in view. I'll have to turn this up. You can do better than that with me. I zoom in on something brighter, I'll have a greater chance of seeing lots of photons. Let's see. There we go. So I've got some photons in view. Right now we're just in regular analog imaging mode, but if I turn into photon counting mode, now I have these display tools that allow me to continue the photon discriminator. Sorry, configure the photon discriminator. And so there are a couple different options you can use. You can do a simple threshold crossing for the photon detection. And let me bring the threshold down. So obviously, simple threshold crossing will just mark a photon detected anytime the signal rises over the threshold. But there are some cases where this isn't as effective. So in threshold crossing, it can be difficult to set a threshold level where you won't miss events such as this one, where there was kind of a double pulse. But at the same time, if I set the threshold too high, there are some events that I'm going to miss because they never exceeded the threshold. So threshold crossing can be useful in some cases, but there are a lot of cases where it's difficult to find a good threshold level that works. So another technique that we offer here is a peak detection method that works by thresholding the differentiated signal. And so in peak detection, I set my threshold in the differentiated signal here. And this algorithm is actually detecting the peak of those photon pulses. And so that's much more reliable given the high multiplicative noise that's exhibited by PMTs. So that's all I wanted to show here, just a couple different ways that you can configure the photon discriminator. If we turn on time correlated mode, which I can't demonstrate here because I don't actually have an 80 megahertz laser, but this interface will then allow you to specify if you want to window your acquisition based on the time the photon arrives with respect to the laser pulse. So there's a lot of flexibility that this interface will give you. It'll allow you to add multiple virtual channels here, like Bruce mentioned, up to 64 that you can use to divide your signal based on the temporal information into separate acquisition channels. And that's one of the capabilities that we're working on extending for Dr. Ali Pasha's latest research. So I'll go ahead and turn it back over to Bruce.
All right, so the last thing we wanted to share with you is we've got a new Mosaic tiling mode coming this year. This will allow you to use a stage to image and stitch areas larger than a single view. We have a lot of requests for this, and I have a brief movie to show here. So hopefully, let's see, I'll start it here. And so basically, you can see first you would do a focus to get an an image that you want to look at or center around. This is just a kidney slide on our confocal microscope, and then you'd select this new tile view, and you disable the live view, and so you've now got your your initial image in the center. And now you can draw, the tile or configure the tiles that you want to get around that initial image. So it does it fairly automatically for you. You're just gonna, tell it the size of the images that you want. And then here, John has actually created this movie and shown that he wants a 3x3, tiled region. And then, you basically tell it to go do its job, and I guess you have to tell it where you want to save the data first, but then you can, give it a command to go ahead and image at all the tiles. So we can hit start in the scan control, and it will now, systematically collect the images in each tile. So this is an approach that will come out, this year, probably, in the first half of the year. And we're pretty excited about it. You have to have good stage alignment and good stages to be able to do this. So you get really nice, well-aligned segments, but it's a feature that people have really sort of wanted and demanded. So that's pretty much everything that we had to share with you today.